Good morning and good day, everyone. My name is Tony. I'm a course advisor and I'll be your host for today's session. Before we begin, I'd like to just cover some few notes so that everyone get the most of this session. On your screen now, this is the notification and sound buttons. So you are able to turn on and off your notification and sound as you wish during this session. Please post any questions under the Q&A function at the top right-hand corner. You will see the Q&A. So if you have any questions that has to do with today's topic, you can also put them there. If they are related to our course offering, you can also put them there. We'll be able to answer as we go along. Okay, so these are some of the common questions that are asked. So everyone registered for this webinar will receive a PDF slide and a link to the video recording within the next 2 business days. So please make sure that you do check your junk folder, spam folder, if the email does not appear in your inbox. And also, we will then provide you with a free digital certificate of attendance for live attendees. So there will be a link and a QR code just after this webinar. So make sure that you stay with us until the end of it to qualify for the certificate of attendance. Just a bit about ECT. So ECT, it is affiliated with the well-established Engineering Institute of Technology, EIT. Is an engineering education specialist. ECT delivers professional certificate to our highest qualification, which will be a master's degree. And also our programs are designed by industry experts, ensuring you graduate with cutting-edge skills that are valued by employers. Our program's content remains current with rapidly changed technology and industry development. ECT is registered and accredited, meeting the Office of Students requirement for course quality, academic standards, student support, and student protection. And our lectures are subject specialists with industry experience and requisite academic qualification. The online platform allows ECT to source them from a large global pool of expertise. So we also offer a unique delivery mode. So we deliver our programs via a unique delivery methodology that makes use of live interactive webinars and international pool of experts, as I've mentioned. You'll also be getting learning support officers that will be assisting you throughout the program. Okay. Event conduct, please keep discussion lawful and respectful. Follow the moderator's directions. Do not share illegal or abusive content. Recording is not permitted unless authorized. Breach may lead to removal and referral under the ECT policies. As we move right along. So today's topic is basics of SCADA and PLC systems. And our presenter for the day will be Dr. Abdu. So he's an industrial automation program leader. Dr. Abdu, you can take over.
Thank you, Tony. Let me take over from you now so we can move on. Right, so hello everyone. My name is Abdulrahman Shaalan. I am the program leader for industrial automation courses or programs at ACT for undergraduate and postgraduate programs. To give you a little bit of idea about my background, my undergraduate degree was in mechatronics engineering, and then had my master's in engineering management, and in my PhD in industrial automation and advanced maintenance practices. I did hold the role of engineering lecturer as a start of my career at University of Sunderland in the UK, managing different modules, delivering different research projects and consultancies with industry partners. I had extensive work with different industries, including oil and gas, food industry, automotive industry, aerospace industry, so you name it really, which gave me really good insights on or into how industry work and how different applications are getting made or manufactured or managed in different sectors. I did hold multiple research projects, supervised many undergraduate and postgraduate theses and projects, which as well was innovative and really interactive applications that are useful to industry. Now I moved on to the ACT, and the reason behind this was how exciting ECT is and how the model is really focused on the delivery of industry standards to students and making education available to everyone. Not you don't have to go to the university, you don't have to attend the class in person, rather than you can learn from anywhere. And the model and the way that it is getting delivered was very interesting and very exciting. And that was kind of the reason behind me moving on to the ECT. So what we're going to cover today, we are going to talk a little bit about industrial automation. It's not very extensive details or in-depth knowledge about industrial automation, rather than we want to know what is industrial automation in general. We want to see how does it work, how is it useful, and how could it be applied in different aspects. We will look into how an automation system in general can be constructed, and we will have a quick look into the programming aspects of it. So to start with, we will look into the history of PLCs. And when we say PLC, we are talking about a device, a programmable logic controller device. And that device came around in the 60s. And everything actually from when we start to think about any intelligent devices that we have in our lives now, all of this started from the 60s. And the 60s was the start or the introduction of microcontrollers and microprocessors and computers in general. So that was the initial point, and this was the third industrial revolution, the way that we can see it. The automation of things, how can things and devices and machines work by themselves? And that was a huge step up into industry and into our own lives as well. If you started to look around you, when you have your TV, you have your washing machine, you have your fridge, you have a little bit complicated, you have your computer, you have your iPad, you have your Apple Watch, you have your phone. All of these devices are the new generations that came from the development from that first introduction of microprocessors and microcontrollers in the 60s. And we heard always about the terminology of Industry 4 and Industry 5, and all of this are different functionalities that have been added. Different things came across with Industry 4, and with Industry 4 we hear about AI, we hear about IoT, we hear about cloud computing, cybersecurity, robotics, all of these different things. But the impact on automation was from the connectivity point of view. So when you start to think about why Industry 4 is a thing that impacted industrial automation, we start to think about, in the past, all the devices were isolated devices. So each device is working by itself, doing its own functionality. It doesn't really talk or connect to anything else. Think about the normal washing machine that you might have at home. It's a device that is an intelligent device. You set it up to whatever the program you want, to how long do you want it to wash, or what the program of the washing is, and it works by itself and finishes, and that's it. Industry 4 came with a connectivity aspect that allowed this washing machine to be connected to the internet. And when you start to connect to the internet, we start to have communication between different devices. So you hear now about a smart washing machine or a smart fridge, for example. All of these devices are built on industrial automation but they started to have the connectivity ability, so they can talk to something else. This is when you start to have an app that you can control or monitor what is happening with your devices, as a very simple example from domestic applications. Our focus today is going to be about or on factories and factories and machineries. And when we have the same concept, how did that impact manufacturing? We start to think about what was there before industrial automation. So before industrial automation, we started to have, or the second industrial revolution, it was about production lines. And how did we start to have all of these fully production lines that can manufacture different things, cars, and this is where it started from with Ford, actually. We can make cars, we can make appliances, we can make whatever the machines or equipment or tools or devices that we have. And when we start to think about a production line, we start to think about it is many stages that are constructed together, and they have to work together with harmony in order to make or manufacture that specific product. So we started to see now, how can we actually manage the transition, and how can we manage the processes that are all linked together? In the past, we used to have, before computers, we used to have something called relay room. And the relay room, because we didn't have any intelligence at the time, that and electric circuits and electronics, that was the only way that we could have managed to control that production line. We want if we are making a car, for example, it's a very basic example. First step, we are making the body. So that chassis of the car has different sides, different parts, and then it moves on from, let's say, in a very simplistic way, that body construction is one step, and then it moves on and it gets painted, and it moves on and gets the engine installed, and then it moves on and gets different parts, wheels, gearboxes, seats, whatever the different, all the different components that goes in the car. So all of these are transitions and processes that are lined up after each other. So how can we control this? How can we control that first process and the transition between that first process to the second, and from the second to the third, fourth, etc.? And that was the whole idea. We used to have this relay room and circuits that can help us to construct such a system. And how the way that you can see it, like how it is with the photo here, you can start to see that a very busy relay room. And you start to think about, well, if I wanted to do any modifications to any process, that's not going to be an easy task. And if anything wrong happened, again, it's not going to be an easy task to diagnose and to fix it. So it was not really an easy job to handle or to deal with, because everything was a mechanical devices. So a device that is taking care of a certain process or a certain timing, counting, whatever the different things that it is taking care of. And there is no programming and there is no intelligence within that system. And that was the whole idea of the PLC. How can we get rid of all of these relays and replace them with a single device? And that single device was the Modicon 84. And the Modicon 84 was the first PLC that was introduced in 1969. So even though it was the first fully functioning PLC, and even though it was not really successful commercially because it had very limited memory, it was still the first success in manufacturing or making that device, the controller, the PLC, programmable logic controller, that can replace all of these relays and introduce intelligence to the system. And then in 1973, that was developed to Modicon 184, and that was the first kind of commercially viable, useful device with better memory and better usability of this of a PLC in general. So let's get here. So when we start to think about what the PLC is actually replacing, you can start to see these devices that got replaced. They still exist because Well, there are many of the machines or processes that do not really require lots of intelligence in them. And they can be just replaced, or they can be controlled and managed by these simple devices that used to be controlled in the past. Like how you can see here, there is these different, just a bit of a zoom in, right? So you can see here at the top that we have counters, and the counters are very useful function, or is a very useful function in industrial automation, because I want to count, for example, how many parts I'm making. I want to stop after certain set of numbers. And something else will be the timers. I want to stay or apply welds or paint that car, if we're going to stick with this car's manufacturing example. So I want the car to be dipped in the paint or getting painted or whatever the process for a certain number of time, or I want the entire production to stop at this stage for a certain set of time, then moves on again. So timers and counters are very important aspects in general within industrial automation. When we think about industrial automation, think about how can we manage the processes and the flow of processes that are linked together. How I want to start a certain process for a certain amount of time and then stop it and then start another process for a certain amount of time, and how can I do the counts and how can I do these different things. Think about the traffic man or the traffic lights that you have. The traffic lights, it's all about managing the traffic. It's not an intelligent thing, rather than it makes a good flow of traffic. If we don't have traffic, all cars are going to have accidents and things are going to be chaotic. So that is the whole idea of the PLC, or programmable logic controllers. How can we manage the processes? Through using that intelligent device. So you start to think about what could it make. So you can have a lot of different functionalities within that PLC. So as we said, you can have timers that can set or start certain processes for certain amount of time, or stop for certain amount of time, let's say for heating or cooling, whatever it is. It can do some arithmetic operations. So it can do additions, subtractions, multiplications, division, whatever it is. So think about the comparison between different elements. I want to compare the values of two different components. Let's say it is a weight scale, for example. So I want to reach certain weight of materials in order to move on within my processes. I want to compare the values of temperature, of pressure, of vibration, whatever it is. You can have data comparison, like equal, greater than, less than. You can have word manipulation, like copying and moving. You can and the communication in sending and receiving messages between different devices to inform the devices with their own status and how can it move onward, forward, or whatever it can be the processes. So as I said, it is all about sequencing. We want to create a sequence of operation, and we want to have freedom in the manipulation of data. So how can we, as I said, how can we change the timers if we did change the product specifications, for example? If it's a car manufacturer, so this factory is making one model now. In the next year, it's going to be a different model. Can we adapt to the same factory to make the different model? And this is going to be the answer for this. Let's keep the questions towards the end, and we can have everything that you have, everything that you have is thinking of answered. It is totally fine. So, as I said, data manipulation and changing parameters and sending and receiving data between different devices. And one of the most important elements, it is the motion and processes control. So it is controlling the motor's speed, direction, and operations, and all of this using inputs and outputs. So when you start to think about, well, how does it work from the inputs and output perspective? Think about yourself as a human. You as a human, you have your brain, and this is your processing unit. This is the device, this is your PLC that processes the data and takes the decision. So what could be your inputs? The inputs are all the things or all the senses that give you awareness of your surrounding environment. So you can see, you can hear, you can smell. All of these different senses are input devices. And these input devices, they go to your brain process them, and then your output devices would be your hands, your legs, so you can reach to stuff, you can move towards different things, you can do different things. So your hands and legs are your output devices. Same thing about industrial automation. When you think about input devices, you can think about all the sensors that might exist. So you can have a temperature sensor, pressure sensor, speed, flow, vibration, whatever the type of sensor that you might need for your own application. And as an output devices would be the motors, can be cylinders, pneumatic cylinders, hydraulic cylinders, thermal actuators, whatever the different actuators that you can think of that can actually act or perform action or real action in the real life. So that is the whole idea of how industrial automation works. So when we think about what are the different types of data or the inputs and outputs that a PLC can work with, we can work with two types of data. So we can work with something called analog data, and the analog data are the variable data, like how we say it with temperature. Temperature is a variable data. So it can be, temperature can be 1 degree, 20 degrees, 50 degrees, 100, 1,000 degrees, whatever the temperature is, this is a variable data. And the same thing for a pressure, for a load, for weight, for whatever it is that you might think of. And the other type would be the digital type of data. So digital type of data or inputs can be buttons. So you have a push button that can start or stop the machines. You have a proximity sensor that can only detects if there is a device or if there is a product or anything in front of it or not. Like how it is with a motion sensor. You might have seen this a lot now, it's everywhere. When you walk into a place and there is a sensor, once you walk into it, the light will go on. So this is kind of a proximity sensor. It detects if there is any movement, it will just light on or turn on the light. So it's a very much of a digital, which means it has the status of on or off. So this is all from the input side of things. When we look at the output side of things, if it is a digital, well, turn on the motor or turn it off. Or as we said with that motion sensor, turn on the light or turn it off. So the whole idea is just it's an on or off application. But when we start to think about the analog inputs, think about the motor speed. So you can have a conveyor belt, and you want that conveyor belt to move with certain speed. So you are controlling the motor speed. So these are the two types of data or inputs and outputs that industrial automation or PLCs can work with. And when they work with this data, alongside with all of the functionalities we just mentioned, that it can do comparison, it can do timing, it can do counting, and it can control the on or off of all of these different outputs, you can start to think about now we can construct an automated system, a system or a machine that can work by itself. So looking into how these devices are programmed, so programming-wise, because it was designated for engineering, and the engineers don't like programming. And that was the whole idea from developing programming languages that are very specific to PLCs. So PLCs in general, it is made of microcontrollers and microprocessors. And these devices mainly are programmed by many different languages like the C, C++, C#, Python, etc. But this is quite difficult to engineers. And that was the engine behind, well, let's make some or develop some graphical programming languages. And these graphical languages are made of three languages. So we have something called ladder diagram, and we have functional block diagram, and we have sequential function chart. These three different languages, quite similar, and they differ in the way that how they suit bigger programs or more specialized people or not, and the application that they are getting used for. And on the other side, Some textual languages were developed as well, like the instruction list and the structured text. And this is more similar to how it is with this Java and the C and C++, etc., but it is in a more simple way. So these are the standards, the IEC 61131 standards that were set for PLC programming languages. So this is kind of an overview and how things are and what is a PLC, how does it work, etc. So I thought I would just show you kind of an example of how would it work and how automation can, or how can an industrial automation system can be constructed. So what you can see here, you can see a pneumatic cylinder. And that pneumatic cylinder, let's can have this marker, this pneumatic cylinder. So this is a cylinder that extends and retracts. It is getting used heavily in industry and in industrial automation because of how it is easy to use and uses air, it's clean energy, and it can be used for the transitions between different processes within different machineries. So it comes in different shapes. So it can be just extension and retraction. It can be rotational. It can be a clamp that can grab things and release them. It can be different applications. So it's a very useful and very common in industry that it is getting used. So when we start to think how such a cylinder or a pneumatic device can be controlled, we have something called the directional control valve. And that directional control valve is a device that directs the air or the flow of the air, whether towards the inlet of that pneumatic cylinder or towards the outlet. And this means that, well, if I did direct the air towards this side, I will extend the cylinder. So it will extend to this side. And if I did direct the air to this port, it is going to retract the cylinder. And that is the whole idea. I want to control the retraction, the extension or retraction. And the same thing for the rotation, really. Well, if it is one port, it's going to rotate right. If it is the other port, it's going to rotate left. If it is a clamp, so if it was one port, it is going to close the clamp. If it is the other port, it's going to release or open the clamp. So that is kind of the whole idea of how pneumatic system can be controlled. The same thing or the same concepts applies for hydraulic systems, except that the main difference that, well, you have oil and that oil has to be circulated back to the tank or from the tank. So with an air, well, you just release the air. So if you are extending the cylinder, what you do, you just open this port to the air to go out and to go outside. And if you are retracting the cylinder, what you do, you release the air from that other side, so you just go to the outside environment. But within hydraulic systems, what you do, you have to control the return of that oil to the reservoir or to take it out of the reservoir. So you have a pump and you have a little bit of a different setup, really. But it is still relying on directional control valves to direct the flow of the oil, whether to extend the cylinder or not. And that's one of the main differences as well between a pneumatic and a hydraulic system, is that the ability for the hydraulic system to control the position of it. So within pneumatics, you cannot really control how much does it extend or retract. What it does, it either extends fully or retracts fully. You cannot really have halfway extension or retraction, which is not the case with hydraulics, where you can actually control how the distance that the piston can travel. So that was one of the main ideas and the main good things, or the differences, really. And again, as well, the higher load for hydraulic systems that it can manage. So this is a very simple circuit, and this circuit is not controlled by a PLC or whatsoever. What it is controlled with, it's controlled by a manual push button. So you have a manual push button here and a manual push button here. So you press the button here, and this is manual solenoid. So it will direct the air to push the directional control valve here to this side. So directional control valves in general, they're made in a very many different shapes and types of them, but let's say you have two status. So one status that the air will flow up, and then you have a return this way. So this is, let's say this is port 1, and this is port 2, and the other direction would be this way and this way. And what you do, you want to control these blocks, and these, based on these blocks, you're going to direct or control whether they extend or retract that cylinder. So what you do is manually you press the button, and if you press the button, you would want this status, for example, and this is going to extend the cylinder because it is directing the air to port 1. And if you press the other button, it is going to direct it to this side, which is going to be the reverse side, which is going to be the retraction of that port. So very manual, and it is relying heavily on manual usage. So let's start to add a little bit of more intelligence to it. So instead of us using normal or basic push button, let's have electric circuit or electric signal to operate this solenoid. So that solenoid, now it is not controlled anymore by just a push button, rather than it receives a signal from the PLC. And when that signal is received from the PLC, it's an electric signal, it will energize an electrical solenoid. And when that solenoid is energized, it is going to be, or it's going to energize either direction or either states of that directional control valve or DCV, how we call it. And you can see this is quite kind of circuitry for it. Let's a little bit see how it is, how can we add a little bit more intelligence. So a little bit more intelligence within that PLC, you can add a little bit of more lights. So you can have a green light for the extension, for example, and you can have a red light for the retraction. So you can see and you have a visual representation of what is the status of this device. And you'll see that a lot within manufacturing equipment, that they have these lights that can indicate whether it is retracted or extended. And this way you can see that it is fully operational device or not. Because if you can't really know if it extended or not, and this is a machine that has lots of different complexities that is going on with it, it's not going to be easy really to detect if there is something going wrong or not, rather than you have this visual element that can tell you what is going on. And this was made easier by the PLC because as well, you can include in the circuit, you can include these lights. Once that cylinder is extended, you will show a green light. Once it is retracted, you're going to show red light. So a little bit more intelligence. Well, you can have an emergency stop push button, for example. This is typically with any manufacturing equipment or machinery. You can have a button that if anything wrong happened, you can press on it to stop everything. And as well, what you can have a horn, and you can have audible alert that can tell you if that extended, retracted, or if there is anything actually went right or wrong, whatever you want this application or these different things to act as now. So you start to see that, well, with automation, now I started to move from very basic, simple system that is just relying, so I clean this, that is just relying on a push button and a person really just sat there pressing that button to extend or that button to retract, into a more of an automated system that it is working by itself. So I don't need that person to be there anymore to press the button to extend or to press the button to retract, rather than the PLC is doing this job. And that's why it is always said that, well, automation is taking away jobs from people. Well, it is taking the jobs that are not really expert or not skilled jobs. If a person has to be there to just press the button, that's not really a useful job to the economy and to the and to humanity, really. It's a basic job that can be replaced by a machine. That person can be trained, that person can be upskilled in order to do more complicated tasks, like constructing the whole system, for example, or maintaining that system and making sure it is working how it should be. So this is one thing, or we looked at one element of that system. Another element would be the programming. Now we built the physical system with the cylinders, with the directional control valves and the lights and the audible alerts and alarms. And what it is there now, it is all about, well, we need to start to do the communication with the PLC. And this is when you start to see that, well, you start to look into how everything is connected to the PLC, how the PLC's inputs and output ports are linked to all of these directional control valves and all of these solenoids in order to create the operation. The other element would be about, well, you need to write the program for it. You need to write the logic. How do you want it to happen? You might want to wait for a little bit between the extension and retraction. It's not just extend and retract straight away. No, you want to extend and then wait for 2 seconds, 3 seconds, and then retract. So a little bit of more of a logic into how things can happen. And what do you want to happen afterwards? You might want to link multiple cylinders together. And this is the whole idea of the intelligence of the PLC. You can do that and create that logic. And you can start to see and visualize how things can be done. So the system is more of smart system and more advanced systems. So moving on, what we spoke about so far, we spoke about a very basic level of control. So when we look about automation hierarchy, we are talking about 5 different levels of automation. First level, or level 0, this is the field level, and this is where you have all the sensors, the inputs and outputs. So you have all the different sensors, buttons, and you have the outputs, the actual motors, valves, cylinders, whatever it is. The second level, or level 1, this is the control level. This is where you have that PLC, what we have been talking about all of this time. So you have the PLC that can control all of these field devices. All of this is based on one single machinery or a system. So what if you want to connect multiple machineries together? What if you want to connect the entire factory floor together? And this is when you start to move into the supervisory control systems, or towards the optimization level, level 2. So you hear a lot, you might have heard of it, you might not. So there is something called the SCADA systems, supervisory control level process optimization. So the whole idea of the SCADA, that you can have an overarching system or software, and that software can connect to all the devices that exist within a factory floor, and it can monitor and control all of these different machineries. You can update the parameters, you can change how they operate, you can monitor their performance and see what is going on. You don't have to go to each machine and see how it is working. If it is a car factory, for example, we have hundreds of machineries that are connected together. You do not really want a person going after each machinery, or one for each machine, to monitor and see or update it or turn it on or off or change things with it. Rather than you want one place, one big room that can have access to all of these different functionalities, and you can just do it from one place. And that is the SCADA system. And that is the whole idea of a SCADA system. Up to this level, we are up to control level. So this is where you stop, or you end up with actually controlling processes. When you talk about level 3 and level 4, which is production level or MIS level, you start to think about higher level of within the company. So you look at the plant control level or production planning and scheduling. So you want to make set number of products today. You want to schedule different things to be happening. You want to control, or you want to plan for the entire operation for the whole month, for example. And this is production level. You want to set and control how production planning and scheduling is working. When you look at the corporate level, now you start to look at resources. You start to look at the connection between different things. So you're looking at the connection with the supply chain. You can connect with the payroll and the employees and operations and the higher level system that controls the entire company. And that is more of an overarching management system that can control and look and oversee everything within that company. And that is kind of the whole idea of automation systems and the different levels of automation systems. It is all about understanding what each level can do and what each level can provide to the company and the way that things can be done. What I want to show you now is how the programming work and how things can be done a little bit instead of just the presentation. So let me try to share my screen so I can show you a little bit of how this can be done. So is this visible to everyone? If someone can say that you can see that software, or can say
I can
confirm.
see it.
Right, okay. So what you can see here, this is a programming software. And this programming software is called codices. So every PLC manufacturer in general, in the past, they used to make their own software to program their PLCs. And that was a little bit of a limiting approach because, well, Siemens have a software called TIA Portal. Allen Bradley, they have something called Connected Component Workbench. Different companies, they have different softwares and terminologies. Well, codices came around as a general use or to be generalized or to be generally used for many different brands. So different companies, instead of making the device and making the software, they started to only think or focus on the hardware, and they can use codices to program the software, like how you can see with mobile phones, for example. You can see many different brands that are using Android, but all of these companies, they're just making the hardware, and then they're using the software, which is the Android, for their phones. So they don't really care anymore about developing the software. It's not like Apple, for example, making the hardware and the software, rather than the different approach of we have the software and any company can use it, and they can only make the hardware. So what I wanted to show you here, this is a sample of a program, and it's a very basic sample. It's just to show you functionalities of how things can be done. But the whole idea is that you can start to see how this is done. So this is a programming environment, and this is a PLC program. And what you have here, you have the ladder logic diagram language that is getting used for programming. So what we can do here is we can write the software, and this is the way that it is getting constructed. Each line of program is called a rung, and this rung is made out of inputs. So all of these ones on the left are inputs, and everything on the right is an output. And the whole idea is each line or each rung, what input do you have and what do you want to happen when that input is energized? As we said, that input can be a push button, that input can be a sensor, it can be a signal that something happened or done already. So if it is a counter, for example, so once the count is finished, so now I have a signal that the count is finished, and I want, based on this, to stop the machine from working, as an example. So when you start to think about it, so as a start, think about this start, it is the start push button of a machinery. So if I want to start the machine, let's log in and get on the simulation working. So just give me a second. Use this. Simulation, 10. So what we have here, and let me just force these devices off. So what we have here, we have a start push button, and let's think, for example, what I have or what I want to do. I have a push button, and when I press that push button, I want to start the machinery. So how do we construct this? And this is the whole idea. And in the same time, what I want to have an emergency stop, like the one we just seen. So if anything wrong happened, I will have that button pressed. When I press it, everything is going to stop. So for example, let's say that this output is going to be a light. When I press the button, I will turn on the light. So if I wanted to do this, now I have, well, this is a specific type of a circuit that is getting built and developed. We're not going to get into depth into how it is getting done, but to show you, for example, how it is done. So if I simulated that, well, I press that button. So what you will see that it did change into the blue side of things. It stores the values in a variable, etc. But eventually, what you can see that the light has started or went on, and you can monitor the values of these inputs and outputs here within that variables table. So you can see that the value is true, which means that it is on, or false, that it means it's off. So for the light, I press the button, and now the light is on. The whole idea of that special circuit that I'm showing you, in a machine or in an industrial environment, what you would have, you have a push button, and that push button, it's not like how you have at home that you flick the switch. Rather than it's a button and it has a spring. So once you release it, it goes off. That button goes off. It is related to safety, health and safety and operations and different things. But the whole idea of that circuit, that once I depress that button, what happens is nothing. The light is still on. So even if I'm not pressing the button anymore, now what I still have the machine or the light on. So how do I stop it? And this is how you would have, or why would you have a stop button or an emergency stop button, different system redundancies together. So if I depressed that stop push button, and this is when you start to see that, well, the light will go off. So this is how kind of a very basic example of turning on or off the light within an industrial automation. And that light can be a motor, for example, turn on the motor. Whatever you're connecting to it, doesn't make a difference, because the software only cares about inputs and outputs. So we thought about, or we spoke about, the times and how can we control the time. So for this rung, for example, what we have, so let's say that, well, I don't want to start the machine straight away. I want to wait for 3 seconds after I press the button, and after I wait for these 3 seconds, the machine will start. You might see this with many different things. For example, with your washing machine. So you have that washing machine, you press the button, and then it will wait for a bit, and then it will start actually working. And this is kind of the same thing. You have a delay timer. So, for example, if we try to test it, so let's turn that one on, like as if this is a washing machine. So if I started this, you can see that the timer output didn't actually go on until the time lapsed. So if we wanted to do this again, and when you turn it off, but let's see how it is working again and monitor the output. So now this is on, but this is not off, and the time is counting. Once it reaches a set point that I did put here for 3 seconds, it will turn on. So this is kind of the application or the way that you are making timers or constructing timers. The same thing can happen with counters, like how we said that, well, after a certain number of counts, what you want to stop the machine after making 100 product, 1,000 product, whatever it is. Let's change this to 3 to just make it quick. So, for example, this is a sensor and a proximity sensor that detects whenever you have a conveyor belt and you have a sensor, and it sees whenever a part moves on. So a part passed by this sensor, this is a count. So let's consider this counter one as that sensor. So if we turn on that sensor, so it is detecting something, you can start to see that, well, the count here is 1. So let's turn it off because the part moved on and it's not in front of the sensor anymore, but we have 1 count. Our set point is 3. And you can see that the output is not on or true yet because I did not reach the set point of 3. So let's count 2 more. So this is the second one passed. So 2 passed on, stop it. So the last one, so let's turn that on. And once we reach the 3, now you can see that the counter output has actually did go on. Now I can replace that counter output with that stop button that I have here. So once the count is done, instead of that counter output, I will have the stop button, which will stop or turn off the light. Now you can start to see how can you link different things together, and how can you have the counters and the timers and the start and the stop, all of these different functionalities work together. And the same thing you can do with comparators for the addition of different values, for example. So what you want to do, well, you made, or you're making whatever, you're working grain, for example, and you are counting how many kilos are you making, and you have a set point of whatever it is, 1,000. It doesn't matter really. But what you can have the count, or that count or the addition visualized or printed somewhere on a screen or something, or you can monitor that thing, or that number, you can have a set number for the values. So 2 tons of grains that have been made, now stop. So you can start to do this with that addition factor or that addition element. So for example, here we have 36. So if we made this 20 for that first weight, and that second weight is, well, let's say another 20, for example. So what you would have here, you can have, and you can have the addition of the value. Once you trigger this, you can start to see now when it is giving you the output, and it is triggering an output for that addition. Think about all the different things that you can do with such a very basic arithmetic operation. The same thing can happen with comparators. So you want to compare the weights or the temperature or the vibration or the pressure between 2 different points. Here we are using forced entry values, but all of this can connect to actual inputs and outputs. You can connect all of these sensors together. You are measuring the temperature sensor of 2 tanks, for example. And let's say, for example, you have redundancy systems. So it's a very critical industry. And instead of having 1 sensor, you have 2 sensors that are measuring, let's say, the same tank. And you want, let's say, the blending or whatever you're doing within this tank of chemicals or equipment, you don't want the operation, or you don't want the operation to work unless the 2 sensors are giving you the exact same number. So here, for example, you can use the comparison. So we have the 2 values are 20, and this is where you can see the compare output is actually working how it should be. So if we turn that off and change this to 30, like as if the 2 sensors are not giving you the same readings. So when you turn that on, and this can work by itself without a specific input, but just for the sake of things. So now we did turn it on, but the output is not on, meaning that, well, the machine is not working, or that mixer or whatever you're doing, it's not going to happen. So now you can have that much of a controlled environment. So if we did change this back to similar values, really, so 20 and 20. So let's try again. Now you can see that the output, well, yeah, both of them are equal. Let's go on, let's turn it on. So that's a very basic way, or the very initial, very basics of how things can be done using specific things. But with these basic elements, you can start to think about how can you construct a complicated system or a big machinery that can do many different tasks together. And that is the whole idea. So I hope that was useful. Stop this and stop sharing as well. I hope that was useful to you and gave you a little bit of insight on how things can be done, and how automation systems is works really, and how can you program a system, and how can a system be constructed. So please do have, if you have any questions, please say. Always happy to answer your questions. So my question is, what is running at the background of these PLC devices that can? It is a microcontroller. Microcontroller or a microprocessor, depends on how they are. That microcontroller that you can see, it is an intelligent device that it exists. The same thing that happens or that exists within the washing machine, within your fridge, within your TV, within all of these different devices. A device that has all of these different switches, micro switches, that can work together to do all of these calculations and do all of these mathematical operations. Also, can PLC be integrated with the ZigBee protocol or LoRa technologies these days? I think you can actually, and the modern ways of communication between different devices do actually allow for this to happen. Would you guys please resend the link with the slides? Right, so this is for Tony, not for me. So yeah, no, you're most welcome, everyone. Is Codices softwares? Yeah, it is an open source software. You can just download it from online. Not difficult. No, you're welcome. So I hope that was useful. Are there other languages apart from Codices? Is the software? It's not a language. So as I said, Siemens, for example, they have something called TIA Portal. The brand Siemens and the brand Allen Bradley, they have something called Connected Component Workbench. So different devices, different softwares, but they all use the same programming languages. So the structured text, as I said, it is much more similar to how it is with the C, for example, or higher level programming languages. And it was basically built or developed for the people that have more enthusiasm with coding. So you will see that lots of its logic very similar to the higher level languages like C or Java or whatnot. So very quite similar to how it is working, and it's basically about using text rather than how we just seen that we are just using graphical elements to do this.
Okay. Hey, Dr. Abdu. Thank you very much for today's session. I think it was very insightful, very informative, and I hope our attendees also thought the same. On the screen now, these are our upcoming courses, ECT's upcoming courses, and on the right-hand side, you'll see the dates when the programs are starting. Or you can also check on our website for more information and other courses. Okay, so on the screen now, this is the QR code for the certificate of attendance. So you are able to scan this QR code and get your certificate of attendance. But I'm going to share also a link on chat, so you are able to then get your certificate of attendance. I've shared the link now, so you can just do that, and you will then receive the certificate of attendance. I'm not sure if there are still any questions, or Dr. Abdu answered all the questions that were there. Is there any other questions, Dr. Abdu, or I think, oh yes, yeah, I think you've answered all the questions. And just the people that were talking about the slides, so it will be sent to your email, the email that you used when registering the session. The slides will be sent to that email. So make sure that you do check your junk folder, spam folder, if it does not appear in your inbox. So on the screen now, this is our contact details. So you are able to check on our website. That is the address for our head offices in Stevenage in UK, and the phone numbers also they are there. You can visit the link on the screen for other courses that we offer at ECT. So let me just leave this here, the QR code, so that you can scan. But I did also share the link on the chat box to claim the certificate of attendance. Okay, we are at the end of our session, and I would like to thank all the attendees for taking time from your busy schedule and attending the session. I hope you learned and you got a lot from this session from Dr. Abdu. Last words of Dr. Abdu.
Thank you very much.
Oh, okay. No, thank you very much, Dr. Abdu, and thanks to everyone who joined us. And you guys have a great, wonderful day.
Bye.
Thank you. Bye-bye.